Alrighty, hi everyone. Welcome to exam 4 final review. I'm sorry for my voice. I feel like I developed allergies overnight. So please bear with me through this hour if you hear me sniffling the entire time. But I see all of your questions in your questions that you want to go over in the chat right now. I'm just going to take a minute or two to write them down. Just make sure I cover the ones that are important. If there are any specific questions that you need, or if there's anything that besides questions you want to go over today, if there's like a general concept or anything that we want to go over today too, please feel free to put that in the chat as well. But I'm just going to look through the chat real quick just to make sure that I am able to cover and game plan what we want to do for the hour. I'll take a couple minutes to do that, so I will just stay a little bit later as well so that I give you a full hour of my time. I just need a piece of paper. Okay. Okay, cool. So it looks like a couple questions. Perfect. Okay, so we're going to start with mock exam B because I think there's more questions for that one than mock exam A. I'll try to hit all of those and then the last questions that came in as well for these. So we can get started. Let's start with, we're going to do mock exam B question 4 first. This one. So okay, so it's this question. I'll write it down. It is how much okay, so with this question here, which says how much energy is required to heat 87.1 grams of acetone from a solid at minus 147 degrees Celsius to a liquid at minus 42 degrees Celsius. So this question, whenever you're looking at a specific molecule or element or something like that, that's being heated from a solid to a liquid, or saying going through a phase change or something like that, you want to think of your phase diagrams. And that's the ones where you have, they look like this. Like this. These are a type of phase diagram. This is temperature on the side. And I believe this is energy on the bottom. And so these will tell you that this is going to be your phases. So the diagonals are always going to be a phase. So this will be a solid here, a liquid, and this is a gas. And then on those horizontal lines, we have a phase change from solid to liquid and then from liquid to gas. So whenever you're seeing something where they give you a specific heat in the question as well, that is also a good indication that you have to use this kind of phase diagram type of problem. This also should indicate if you have a specific heat, which is like your C value, that you're going to use Q is equal to MC delta T. And then in the question as well, they also give you the heat of fusion and the heat of vaporization. So that's H vap or H fuse. If you see that, that should also point you in the direction of using this type of graph. Okay, so I told my students that showed up yesterday, I kind of think of this as like a roadmap. So I always like draw this little stepwise function on the side of my paper whenever I do these types of problems, and I kind of pick a start and a finish line. So we are starting at a solid at minus 154 degrees Celsius. So we're down here. That would be our starting point. We go to a liquid, so we say that we end up as a liquid at minus 42 degrees Celsius. And so we might end up over here. I am so sorry, I'm sniffling so much. So then we have to go through this point where we go through the solid, go through the phase change, and then through the liquid a little bit as well. So looking at this, we also are given that our T melting is minus 95 degrees Celsius. Okay, so when we look at this type of question, we need to say, okay, I need to get from minus 154 to minus 95, go through a phase change to melt my acetone, and then get from minus 95 to minus 42. Okay, so we have to go through 3 different steps, right? This solid, this phase change, and then this liquid component. On our solid and liquid phases, where do we, or what equation are we going to use for that? What equation do we use on just solids and just liquids or just gases in this type of question? Good, right? That's that Q is equal to MC delta T. Perfect. Okay, so we're going to have Q is equal to MC delta T. Oops. Delta T for the solid and for the liquid. And what do we use in order to do a phase change from solid to liquid? What equation do we use there? Does anyone remember? Good, yep, so it's going to be that heat of fusion. So we also are going to use plus M delta H of fusion. Fusion is if you go from liquid to solid, but so the direct opposite would be your melting temperature. So that's going to be used in both of them. Okay, so we can set this up. I'm not going to do all the math, but I'll show you like how you would set it up in this way. So from your question, we know that we have 87.1 grams. So for this mass here in our MC delta T, does that need to be in grams or moles? Good. It's going to be in grams. So your solids and liquids, just your pure phases, are going to be in grams. So your Q is going to start off with 87.1 grams times the specific heat of your solid, which is 1.65 joules over grams times Celsius. And your temperature change is going to be your final minus initial. So our final is going to be minus 95 degrees Celsius, because that's where we have to melt our acetone, and then minus negative 154, which is our initial. These do not need to change to Celsius or to Kelvin, because you're in Celsius, and then your specific heat is also in units of Celsius. And then we'll do the same thing for the liquid, and your liquid is 2.16 joules times grams times Celsius. And this change is from minus 42 to minus 95. Sorry, that got bunchy over there. Okay, so that's your component for MC delta T for both your solid and your liquid. And then we're also going to add our delta heat of fusion. For this is 7.27 kilojoules per mole. So before you can use your mass in your equation here, you either have to convert your grams to moles using the molar mass, or your moles to grams using the molar mass. So it doesn't matter if you change your grams or if you change your delta heat of fusion into grams. So either one, but I'll change this to grams. So it would be 87.1 grams. We're going to use our molar mass of 58.08 grams per 1 mole times our heat of fusion, which is 7.27 kilojoules per mole. Okay, and we would add all of that up. And that would lead us to choice D, which is eventually 29.4 kilojoules. Okay, please be aware that this is in kilojoules and these are in joules. So you do have to change one of those units to kilojoules or to joules. I would personally change the kilojoules to joules, and then at the very end, then change it back to kilojoules to find your answer in the multiple choice. Any questions on this type of problem and how to identify this type of problem? Good question, Sydney. So we have to include this fusion part, because when we're going through our stepwise function on our graph, we have a solid portion and we have a liquid portion, but we need to take it from the solid to the liquid. So we need to say how much energy is required to do that phase change. During a phase change, the temperature is not changing, and we're just putting all of our energy into changing the phase from solid to liquid, or from liquid to gas. Yeah, of course. Any other questions on this type of problem?
Just to clarify, so when you're doing this type of problem, usually what you're looking for in the question is like when it says solid to liquid, or like another phase, like a phase change. Is that what you said?
Yep, a phase change is
Okay.
good. And then she will give you all of the constants that you need. So if you see specific heat given in your question, then it would then it like that indicates that you have to use Q equals MC delta T.
Oh, okay. Okay. Sounds good. Thank you.
Yep. So Maddie, this question is mock exam B question 4. And Maya, yes. So if they said that you were going from liquid to gas, this would be the same exact question. You would just have slightly different constants, because it'll be specific towards the liquid and the gas constants this time. And you would use the delta heat of vaporization, because you have to take it from the phase change from liquid to gas. And yes, that's a negative 95 in the parentheses next to negative 42. Any other questions on this one? Okay. I think we're looking at free response questions. So let's do number 9 from the practice exam. So this is question 9 from mock exam B. And so we are given, oops, that's not what I wanted. Okay, I paraphrased this question, but essentially you are given the equation 2H2 plus O2 goes to 2H2O. Always remember that if you're given a question, even if or a chemical equation, even if she says it's balanced, make sure it's balanced. But you're given this balanced chemical equation and they're saying in a volume, in liters, you have excess H2 and you're reacting with 1.63 liters of O2. And we want to know how much volume of the H2O is produced. Okay. So this ties into the flow chart that she mentioned in class yesterday and what we can use in order to get from, the reactants to the products using mole ratios. So when you're looking at this, when we say we have excess H2, this is eliminating that limiting reagent question. We don't have to decide which one produces the less product. We know that our limiting reagent is our O2 of 1.63 liters, okay? Whenever we use something in the chemical equation to get from reactants to products, we always know that we have to work in moles. So we are given a volume, we have to get into moles. How do we get into moles? What equation can we use here? Remember, we're talking about gases. We're given that we're at STP. We're given a volume. What can we use? Good, awesome, right? We can use PIVNERT. So if we use PIVNERT, we know pressure because we're at STP. What is, I guess, did she give that to you? Yes. So she gives you that pressure is 1.00 atm. Do we know our volume? Yes, we do, right? This is the 1.63 liters. Do we know our moles? No, we do not. So this is what we need. We know R, this is 0.08206 liters times atm over mole Kelvin, which is given to you. And then we know temperature is 273 Kelvin. Okay, so we can solve this for the number of moles of oxygen. So if we do this, N would be equal to this bad boy here. I don't remember how many number of moles that is. Could someone throw that in the chat real quick? What are we thinking? Awesome. Megan, I do believe that would work as well. Okay, so we have our moles, unless someone else tells me otherwise, that this is how many moles we have. So we're going to take, right? Okay. I think it should be small boy. Yeah, okay, cool. Thank you. So it's 0.07272. Sorry, I did this earlier. I just don't remember them. I don't have my work in front of me. So this is going to be moles of H2 of O2. What is our mole ratio to get to moles of water? Beautiful. So we have 2 moles of H2O for every 1 mole of O2. This will get us to moles of H2O. And then to get to the volume, we're just going to do the opposite of what we did over here. Okay, just reverse it. So instead of finding our moles, we're going to use our moles to find volume. So this will be here. Volume will be equal to the number of moles, so the 2 times 0.07272 times 0.08206 times 273 divided by pressure, which is again 1.00 atm. And so we get 3.26 liters of H2O. Okay, this was a longer way to do this question. Exactly. Tia, that's exactly what I was just about to say. So this is a long way to do this question using Pivnert. But what you can see is that, hold on, where's my highlighter? Highlighter here, right? In the first step, we have 1 ATM, 273, and this R value. We use that, multiply by 2, and then use that with the R value and 273, and then 1.00 again. So whatever you multiplied and divided by the first, you do the opposite going backwards. So what this essentially boils down to is just your volume times 2, or times that mole ratio. So if we had something where you had 3 moles of oxygen and 2 moles of water, then it would be 2 over 3, and that would be the same thing. So this is another, so you can just look at this way. This works out because we're at STP, we're not changing any conditions between the reaction of the reactants and the products. So this essentially just boils down to the liters times the mole ratio to get you the volume of your products. Okay, but this is a way to prove it to you using Pivnert if you get stuck, if you don't remember like what this question is asking for as the first time you look at it. Okay, great question. So STP is a great type of question, or is a great like buzzword to get you that you are in some sort of gas question. And then if you're in gases, you should be able to use PV is equal to nRT. And that, so you can just kind of see what you know in that equation first and see if that helps you out. If you're going anything from reactants to products, this should indicate that you need to use some sort of mole ratio. And so here we have excess H2O reacting with O2, how much product is produced. And then And those two things, so I would say reactants to products and then STP indicate that you're doing a gas reaction where you need to use the mole ratio. And yes, so we multiplied 1.63 liters times 2. I guess that's a little deceiving. This is actually 2/1, which is the mole ratio that we see here and here. Okay, any other questions on this type of one? Like the yellow portion, I think it is. So the black writing that you see here is all going to be the longer way to do this type of question using PV is equal to nRT in all of your gas equations. What I highlighted in yellow is showing you that what we did to find moles, we then undid when we went to go find volume. So what we boiled down to at the end of this question is we're just taking our liters and we're using the mole ratio to get to the volume of the products as well. So the volume of the reactants can be used with the mole ratio directly to get the volume of the products. And that's because of Avogadro's law, which states that STP, volume, and moles are related to each other. So if you have 1 liter or 1 mole of something, it's going to occupy a certain volume. And then if you double that, then it will occupy twice as much volume. Yep, and leave the answers in liters. Caroline, I think that's correct if I'm thinking the way you're thinking. But basically you're just using the mole ratio directly with the volume. You can, but it would just be the same. It would be the same sort of setup. If you're given the product over the reactant, and you can just go work backwards. So you can still use that mole ratio where like water would be on top, and then that would be your starting. You would use the mole ratio of oxygen to water, and then you would end up in your oxygen. It's just working backwards, but the same rules will apply forward and backwards. Yep. Okay, any more questions on this type of question? Okay, we're going to do question 11, and then we'll go to question 6 from mock exam B. Okay. Okay. For this question here, we say we're starting with 1.323 moles of H2, and I want to know how much heat is released in kilojoules from this reaction. So when we look at this question, it's going to be very similar to the last problem we just had. And when you're given a delta H for a reaction, I like to think of this first as, is this going to be a reactant or is this going to be a product? So when we think about the enthalpy of a reaction, this is for one reaction. So if you just take this reaction, one reaction of these will produce negative 91 will produce 91.8 kilojoules of energy. Okay. So if we're producing a energy, is that going to be a reactant or a product? Right? Do we need to use it first, or are we going to give it off afterwards? Good. It's going to look like a product. So if we were to write this as like a product, we could say we had N2 plus 3H2 going to 2NH3 plus 91.8. Right? Because we're saying we're giving this off. If it had a positive energy, then we could say it was a reactant. So it would be on the N2 and 3H2 side. Okay, so now it kind of looks like if this was its own entity, that 1 mole of N2 would produce 1 mole of 91.8 kilojoules of energy, right? That's what this is kind of showing us now. So now you can just kind of think of it and treat it like a product. So if we are starting with 1.323 moles of H2, what can we use in order to find how much energy is produced? I can't answer my question. Yep. Right, we're going to use a mole ratio, right? It's not going to be exactly a mole ratio because we're not going from moles to moles, we're going from moles to energy, but this energy that's produced is for 1 mole of a reaction. So we could say that we have, for every 3 moles of H2 that's used, we produce 91.8 kilojoules of energy. Did we get to the units that we need to? Are we finding the answer that we need to? We are. Spoiler alert. So this gets us similar to the last question we just had, where we just used our mole ratio down here, right? We used this mole ratio to find our moles of H2O. This, we're using our mole ratio to find the kilojoules of energy produced. Okay, so this is why it says 40.5 kilojoules produced first, and then the negative 40.5 kilojoules is accepted. It's because that produced is saying that it will be released. So that is taking credit of saying produced as the negative value. So this is just 40.5 kilojoules. Whenever you have a question where you're asked about, so Maddie, it can either be positive and then you say it's produced, or you can just say negative 40.5 kilojoules. You don't want to say negative 40.5 kilojoules are produced. Right, so you want to say 40.5 kilojoules produced or just negative 40.5 kilojoules. Okay, so whenever you see this type of problem in it, you would say that you're looking for the moles of a reactant or product and then seeing that you're given an enthalpy of reaction. So if this was slightly different, to answer Sydney's question, right? How would you do the problem if the kilojoules in the question were a reactant and not a product? You would do it exactly the same way. It would just ask you slightly differently. It would tell you, if you start with 1.32 moles of H2, how much energy is required to produce 91 kilojoules of energy or something like that, right? It would ask you for the requirement instead of the production. But the same thing could be applied, right? We could say that we had 1.323 moles of H2. And then it would be, 91 still, 0.8 kilojoules over 3H2 is equal to 40.5 kilojoules. So it would have requiring 40.5 kilojoules. Yep. And that way it might also say, like, you want to produce or like how much energy is required to produce 1.232 moles of NH3, right? Instead of saying that you have, you're starting with the reactant and ending with energy released, you're starting with a certain quantity of energy and you're seeing how many moles you can produce from that energy. That would be like a reactant first and then moles afterwards. Okay, questions there on this type of question? Feel a little bit more comfortable identifying this one? Okay. So I want to do this one first, because now let's do question 6 from mock exam B. So this one is, okay. So here's this question. And we have when 5.5 grams of barium solid is added to 100 grams of water in a container open to the atmosphere, the reaction occurs and the solution raises from 22 degrees Celsius to 61.6 degrees Celsius. And your specific heat is 4.18 joules divided by grams times Celsius. And we want to know the delta H of the reaction. Okay. So using what we've talked about already, we're given a specific heat, we're given the temperature change, and we're given just a reaction in general. Oh, I didn't write the reaction down. Sorry. This is. Okay, and we're given a reaction. So what do we think equation is needed, or what equation do we think is needed for this question? There we go. Brain is working again. Right? Given what just the question, what do we automatically think of? Q. Good. Q is equal to MC delta T. This specific heat portion here should be your key word to think Q is equal to MC delta T. Okay. So now you kind of have to think, okay, I'm going to use Q is equal to MC delta T. What do I know from this question? We're given the specific heat. That's a constant. So we know this already. This will be 4.182 or 418 joules times grams times Celsius. Do we know what our delta T is? What is our delta T? Awesome. Perfect. So we got both points in there. So this is 61.6 minus 22. We want final minus initial always. So 61 is our final. It starts at 22. Do we know what our mass is? Good. So it is 105.5. Why is it 105.5? Beautiful. Yep. So we're taking our system and our surroundings. It's the solution, so it incorporates everything in there, right? Our specific heat, the wording of the question says in specific heat of the solution is 4.18. So we want the solution is everything involved in terms of the particles that's being dissolved and the water that it's in. So we want to use both of our masses for that one. Okay, and do we know Q? Now we can, right? We have everything else on the other side of the equation. We can solve for it. So what do we get for Q? Good. So let's start with 5 sig figs at 17.269 joules of joules period. Okay, but do we see that answer choice on the multiple choice? No, right? Because what should be our units of delta H, right? Did we solve for delta H? That's our question here. Did we solve for delta H? No, right? We solve for Q, which is just joules. We want delta H, which is kilojoules per mole. So what are we dividing by to get the moles of, or to get the kilojoules of mole of our solution? What is that mole component? Yes, beautiful, awesome. So this is, we're going to be using the moles that we have of barium. Barium is considered our system because it is the reaction that is occurring for delta H. So we just want that specific barium component that is being dissolved. So we'll divide by the moles of barium, which I think is 0.04005 moles. And we just use the molar mass off of the periodic table to solve for that. So we took the 5 grams or the 5.5 grams and then divided that by the molar mass of barium to get our moles. And so what did we end up with our now delta H? Yep, good. So we have to convert our joules to kilojoules, and then we'll divide, so we get 431 kilojoules. And then it wouldn't change for a coefficient because we were given a set number of barium grams, and so there's a set number of moles we can have. So the coefficient would not matter here. But good question, Jeffrey. Okay, right. So that was going to be my next question. We got a positive 431 kilojoules per mole. But if we look at the answer key, we know that this is not the correct answer, right? We know it should be negative. And so it has to be negative because if we look at our temperature of our surroundings, we see that we go from a 22 to a 61. So our surroundings are being heated up, which is a release of energy. It has to occur in order for that to happen. So our delta H has to give off that heat. And so in order to give off that heat, in order to indicate that heat is being given off, we must change this to a negative 431 kilojoules per mole. And we divided by barium again, because we need delta H units, not Q units, and that's in kilojoules per mole. Yeah, so a good question came in. Someone said the solution was raising, and that is considered our surroundings. So that's why that changes. We got 17,269 because we plugged in the 105.5 grams multiplied by the specific heat multiplied by our delta T. We like solved the MCAP portion of Q equals MC delta T. We got the 0.04005 by using the 5.5 grams of barium and its molar mass to get to moles of barium. And then joules to kilojoules is the 1000 joules is equal to 1 kilojoule. So for it to be positive, it would have to, your surroundings would have to decrease in temperature, because that means that your reaction that was occurring had to require heat. So it was requiring heat from its surroundings to allow the system to go through. So it would be taking heat from the surroundings to use in the system. Here, our system is emitting heat. So the delta H of the reaction is a negative. If our temperature went from 61.6 to 22, then that would be a positive delta H. When would we know that the water is the surroundings? So your reaction is considered your system. Anything else around it is considered your surroundings. So we're just looking at barium dissolving in this case. And so that is going to be your reaction, which is then considered your system. And so your water that it's dissolving in is your solution. My numbers might be a little bit off. I just used what was in the chat. I don't have my work pulled up. So if your numbers are a little bit off, that's okay. It should get you to around the same answer that the multiple choice is on. Okay, so why this is negative? Our solution, which is everything that it's incorporating it, is raising its temperature from 22 to 61.6. So that means it took in energy that was being released by the reaction and increased its temperature, right? It got warmer because it was an exothermic reaction. The reaction that's occurring is going to be telling you if it's a positive or negative delta H. And so in order for the solution to increase its temperature, energy had to be given off by the reaction, exothermic. Exothermic reactions are always negative. And so that's why we need a negative delta H for our answer. Yes, if the change in temperature was 61.6 to 22, then it would be a positive delta H. Does that help clarify that? There's also one on your exam, mock exam A, question 8, I believe it is. That's very similar to this one where you do have to change that sign. And then we use this formula for this problem because of the specific heat. The specific heat is always going to be that C component of MC delta T. And so whenever you see specific heat, you should use Q is equal to MC delta T. Yeah, absolutely. Does this help clarify this type of question? Yes, okay. Awesome. Yeah, so good question, Samantha. So if it was from 61.6 to 22.0, then delta T would be negative. That is correct. So your delta T would be negative, which means your Q is negative. So when you divide by your moles, you end up with a delta H that is also negative. But we know that our surroundings went from 61.6 to 22 in that case. And so we know that we have to, again, switch our sign to be positive because it was requiring heat from the surroundings to allow the system to go forward. Okay, and then, so if you're looking at mock exam B question 7, I'll do that question real quick because we can explain that and then we have time for one more question. So for this, I'm just going to read it out loud instead of writing it down. So it says consider two balloons, one filled with H2 and the other filled with N2. The balloons have been filled to identical volumes under the identical temperature and pressure conditions. Both gases may be considered to be ideal. Which of the following statements is true? So D answer for this is the hydrogen balloon contains more moles of gas than the nitrogen balloon. What we know from Avogadro's law is that if they occupy the same volume, they will have the same number of moles in their container, right? 1 mole of container or 1 mole of something will occupy 22.4 liters. So if you consider both of them to be at 22.4 liters, both of them must require 1 mole to be in both of them. So that the same volume, they have to be at the same number of moles. And if you look at it in terms of PV is equal to nRT, they say that you're under the same pressure, volume, and temperature conditions. So in order to get R to remain the same between both of them, your N must also be the same between both of them as well. Does that help make sense for that one? Okay. I think question 12 I saw from mock exam B a lot being asked as well too. So we'll end with that one. Let me go back to that question. Okay, so this is enthalpy of formation. Okay. So this is going to be question 12 from mock exam B. I think. Yes. Okay. So this is enthalpy of formation. And we have C6H6 plus 4H2O goes to C3H80 and O2 gas. So from your exam booklet, we are given that we have this chart. Okay. So we are given these 3 enthalpies of formation, different than bond enthalpy, but you're also given this equation as well, where you're the delta H of a reaction is the products minus the reactants. So for this, you basically, it's more of a plug and chug type of question, and realizing that you're doing an enthalpy of formation question and need to use that chart over anything else. So you also want to know that your delta H reaction is going to be the sum of your products minus the sum of your reactants. This equation is given to you on your formula sheet. And then, so the only thing you else need to remember for your enthalpy of formation is that, like, elements, so your diatomic elements, O2, N2, F2, that stuff there, require 0 enthalpy of formation. So within its elemental state, it does not require an enthalpy of formation. So your delta H of your reaction, you're just going to sum your products using the coefficients. So it'll be 2 times negative 318.1 minus the sum of your reactants. So this is going to be 1 times 49.1 plus 4 times negative 285.8 And this is just to plug into your calculator afterwards. And so your delta H of reaction will be 457.9 kilojoules. You are multiplying by its molar coefficient, so that 3, that 4, or that 2. So it does not end up in kilojoules per mole. It is just the kilojoules. It is from your molar ratio from your chemical equation. I forgot the word for that. Yep, these values will be on the formula sheet, as well as this equation. Does that clear up this question? This is very similar to bond enthalpy or bond formation questions, except that one is going to be reactants minus products. You have to look at how many bonds are being broken and how many are being formed. But again, also given to you on your formula sheet. Okay, anything else from this question? Okay, and then I'll do the last one. I think it was 14. So 14 from mock exam B is going to be very similar to the one we just did. It's just using the other chart that's provided to you on your formula sheet. So I would try that one on your own. I'm going to do a partial pressure one. You don't need 11 anymore. I forget what I was looking at. Yep, reactants minus products. 11 on A. So 11 on A is looking at partial pressure. Oops. 11A is partial pressure. So for this, you're looking at P total is equal to P1 plus P2 plus P3. And so you're saying that the sum of your partial pressures will equal your total pressure. So if you know that you have a total of your P total is equal to 5.92 times 10 to the negative 3 ATM, you know that if you divide this by its P1, we'll say, that'll be equal to 2.7%. So you just have to multiply 4.92 times 10 to the negative 3 by 0.027, and that'll help you get your partial pressure for that one. 8. Okay, 8 is good. So this is 8 on A. So this is looking at 0.951 grams of CH4 and 0.875 grams of F2. This one is looking at mole ratio and partial pressure. So we know here that P1 over P2, or not P1 over P2, P1 over PT, the total pressure, will be equivalent to N1 over N total. So this is just you saying you need to convert this to moles and this to moles, sum those two moles, and then divide one by the other. Divide your partial moles over your total moles. That was for 8A. Okay. So it is 6 o'clock, so I can stay for a little bit longer. Yes. Yep, and this video will be posted once I get the link back from Zoom. So you can look back at this again as well. Yep, of course. Okay. So I'm just gonna say my concluding marks right now, and then I'll stay for like another 5 minutes or so to help anyone else that wants to stay. But I just want to say thank you for coming for this. Good luck tomorrow. I will be available if you have any questions between now and then until the exam. You can please email me and ask me any questions. This video will be posted on Canvas once I get the link from Zoom, and upload it to YouTube real quick and send it to Dr. Altamos. So hopefully I did this a little bit earlier than usual, and that'll be up sooner to go back and reference that. I want to thank y'all for a wonderful year. This has been so much fun. You have this exam and a final left over, so you have a couple more days of classes left. You're almost there, I promise. You only have three days left. You have to show up to this. I hope my sniffles go away. I'm so sorry that I'm so sniffly. But it's been a wonderful year, and I hope you do super, super well tomorrow. I'm so proud of all of you. You've worked very hard. I've loved being RIA, so congratulations. You survived one semester of chem. If this is the end of the road for you, good luck. I will be doing this before the final as well, but last real exam. Thank you so much. People that need to leave or go, you can leave now. I'll stay on for a couple more minutes to answer some questions. Thank y'all so much. I appreciate it.
Hey, Allison, could you
Yep.
do number 14 on the FRQs really quick?
Yes.
Thank you.
Tissue. Okay, why is answer 13 on exam A positive? Let me answer that question real quick, and then I'll do number 14. So Sydney, that's very similar to the question we did with the barium and the solution. So same reasoning applies there for that question. Where you have to like change the answer at the very end. I believe it's the same if I looked at that quickly enough. Yeah, very similar. It's just the reverse this time. Instead of making it negative, you have to make it positive. Okay, and then this is going to be question 14, exam B. So this one you're looking at C2H4 and H2 going to C2H6. And this is delta H reaction equals negative 31 kilojoules. Okay. Okay, so for this question, it's important that you write out the actual structures of these products and reactants. So C2H4 is going to be C2H4. H2 is just going to be this. And C2H6 looks like this. So these are your reactants going to products. So when you're doing bond enthalpy, it's always going to be the bonds broken minus the bonds formed, which essentially comes out to your reactants minus your products. Oh my God. I took an allergy med. I think it got worse. Anyways, so the bonds that need to be broken here are CH bonds. I'll highlight them. Are CH bonds, a CC bond, and then this HH bond. So you want to set this up so it's how many of each bond is being broken and how many of each bond is being formed. So when we sum this up, our delta H is sum of bonds broken minus the sum of bonds formed. So I believe you're given a yeah, you're given a bond enthalpy on your exam booklet. Let me just scroll to that real quick. Okay, so we have CH is 411, CC is 350, and then CCC is 810. So do you want to continue or do you feel good after that?
I mean, I'm good after that. I think I just
Okay.
had it backwards because I ended up with like 393. I had it, I think, as formed minus broken.
Yeah, so it's different than like the usual where we always usually do like final minus initial. This one's a little bit different where it's broken minus formed. So it ends up being reactants minus products. But yeah, so if you do that, then you just sum up your yes, I could also continue. So your bonds broken are going to be 4 CH bonds and then 1 HH bond. And that's going to be subtracted from, I'm sorry, and you have one more. So then you have 1 C double bonded and then 1 HH bond. And then you have minus 6 CH bonds being formed and 1 CC bond being formed. So you can use these equations or these formulas over here, and this will all be equal to the negative 31 that were given in our question to begin with. And you can solve for what ends up being X. So you can just plug in the values given and then solve for X there. Kira, does that help you with continuing? Okay, beautiful. So if it says the solution is changing its temperature, then that is going to be your surroundings. If it says the reaction is changing temperature, that would be your system. Number 4. Wow, guys, I think I'm dying. Katie, remind me what number 4 was, and I'll go back to it real quick. Was it this one? Was this number 4? I think this was number 4. Yeah, okay. So what part is tripping you up? Or I could just look at this too, if that's all that's needed. Okay, I'm gonna hang out for like 1 or 2 more minutes if you have any final questions, and then I might take a nap because I'm dying. Okay, perfect. Yeah, of course. Okay, I will call this good at like 6:10-ish then. Thank you so much again, everyone. Good luck tomorrow. Absolutely. Let me know if you have any questions. I will be around for a little bit and I'll answer them tomorrow morning at the worst case scenario. Thank you so much. I hope I feel better too. I hope if anyone's sick, you feel better too. Awesome. Thank you so much. Have a great night. Good luck. Bye.